Hello, everyone. Welcome back to the DDLC seminar series organized by the IDS Lab at Cornell University. And today's talk is going to be about hybrid representations for robust and complex decision making. And it's a pleasure to introduce today's speaker, Professor Nicholas Roy. And Professor Roy is the Hunsaker Professor of Aeronautics and Astronautics and a member of the Computer Science and AI Laboratory at MIT. He received his undergrad in physics and cognitive science and did his master's in computer science from McGill University. And then he went on to do a PhD from CMU in the field of robotics. He's made research contributions to planning under uncertainty, machine learning, human computer interaction, aerial robotics, and he's also founded a cool project called the Project Wing at Google X Moonshot Factory, and he also serves as the autonomy architecture lead and as a principal software engineer at ZooX, which is an autonomous driving company. And without further ado, I'll let Dr. Roy take on the talk.
Thank you very much. It's a pleasure to be here. Always a pleasure to talk to people at Cornell, lots of good friends and colleagues over the years. What I want to talk to you today about is some work that I and my students have been doing for the last several years in really trying to get at the next level of autonomy out of our systems. So we as people are very good at navigating around our world, and we share information and we remember where things are. And this is an example of a Google map type representation. Many of you may recognize it as being from the Kitty data set. And this is the kind of thing that we use all the time these days to navigate around parts of the world that we might not know very well, or even sometimes when there's traffic, parts of the world that we do happen to know very well. But what's interesting is that relatively few of our robots ever actually use this kind of map for navigation. Some do, especially with the advent of self-driving cars, but most of the robots that we certainly use in academia tend to be given the kind of map that looks like this. So this is a map of essentially the same part of Karlsruhe from the Kitty dataset, but it's very different in both quality and quantity. It's a smaller part of the world for sure, but it's also got a lot of different kinds of information. It's very dense geometrically. It's very, very highly accurate in terms of the geometry. It also contains a lot of information, a lot more information by virtue of being dense than we encode in those other representations. And what's interesting to recognize is that if you give this kind of map to a lot of our motion planning algorithms that we deploy in our robots, it's simultaneously too much and not enough information. So yes, it encodes the geometry of the environment, but it doesn't encode a lot of other signals that are useful for navigating. But at the same time, it encodes an awful lot of the geometry that overwhelms a lot of our planning algorithms. And if we want higher level missions, we want robots to do more than simply navigate around our world, then we need to think hard about the kinds of information that we give to those robots. So the kind of thing that I'm after is these videos here show, or both videos if they play, both of these videos show an experiment that we did at West Point in upstate New York last fall, where the idea is that you have a team of robots that have to go and carry out some kind of mission that's specified by a human commander. This might be, this is West Point, this is an Army-funded project, so you can imagine what the military applications are. But even civilian first responders might actually need robots to go and fan out and explore an environment, either looking for suspicious packages, suspicious objects in the environment, or looking for people who might be in distress in some kind of disaster response scenario. And so if you look at the language of the specified here, it's at a qualitatively higher level than what we would see in that kind of map that I showed a second ago. There's objects, there's kinds of objects, there's the idea of securing an area. What does that actually mean in terms of what we want of the robot? And then rendezvousing at the tree in the road, that requires reasoning about all these different kinds of trees and where they are in the world and what it means for the robots to actually collaborate and come together. And so this kind of mission is a real challenge for a lot of the autonomy systems that we see deployed on real robots these days. And it's useful to think about the actual computational architecture. And this figure is one that I've shown many times before. If you've seen me give a talk, you've seen me talk about some of these issues. And it's, first of all, important to recognize that there's often different representations at work in our autonomy systems. At the sort of closest to the sensors and the actuators, we typically have a control loop that is shown down here in this box here, where we have sensor data going into some kind of estimator that maybe is giving us a pose of the robot or maybe a pose and a map of the environment at the same time. And then that goes into some kind of planning system. If it's a dynamic environment, we might also be predicting what the other agents around us are going to do. And then that planning system generates some kind of trajectory that is then followed by a controller that then sends controls down to the motors. And this typically happens at a relatively fast duty cycle and is the kind of thing that works extremely well in our robots. This low-level control exists in pretty much every single operational robot that exists today, whether it's a self-driving car, a factory robot doing assembly, whether it's a drone doing some kind of inspection. This is the kind of technology that we've studied for decades and we know how to deploy really well. But it's really only capable of doing one thing, which is getting a robot from one place in the configuration space to another part of the configuration space, ideally satisfying all the kinematic and kinodynamic constraints of what the robot can do and trying not to hit obstacles, etc. But if you want to do something more complicated, let's say you're a self-driving car that's actually like picking passengers up and dropping them off and navigating through the environment of the city, then you typically have to abstract this to some higher level representation like that Google map. And then we encode symbolic states like we're approaching a place in order to pick up a passenger, we're approaching a place in order to drop them off. Maybe there's like symbolic information in terms of like this is a school zone, we have to like modulate our speed, etc. And that sits on top of this low-level execution engine sequencing goals in order to accomplish a higher level task. And this upper level symbolic executive also tends to work really well. But there's a lot of the time we get into issues on how these two particular symbolic representations and the lower level control executive actually interact. And I'll talk more a little bit about that in a second about what those issues are. I do want to say that with the advent of a lot of very, very large models for machine learning, we're actually starting to see the emergence of different architectures. We're starting to see architectures that look exactly like this, where we have a sensor that's feeding raw sensor data directly into a learned controller, and that's feeding directly into motors. And this is, if you're a fan of deep RL, then you're very familiar with this. And we're even seeing some number of robots that are actually starting to be deployed with this kind of architecture, where like that symbolic representation is just giving a goal down to some learned controller. And there's a self-driving car company called Wave that is making its business case and its operational model conditioned on this particular architecture. And without making a value judgment between these two architectures, we can actually look at the pros and cons of these. So on the left, we have the first architecture I showed, what's sometimes referred to as like a classical architecture. I don't think that's really an appropriate designation. It's more like structured optimization. We are actually running some kind of optimization in here in order to generate a prediction or planning, do prediction and generate a plan, and then we follow with the controller. And then we have end-to-end learn policies that take the sensor data and learn the controller directly from that sensor data to motors. And there are actually intermediate architectures that exist between these two. But we can think about the trade-offs between these. On the one hand, the structured optimization is usually interpretable. We're estimating our state in some kind of map that we understand. It's usually easy to provide guarantees in terms of correctness of the plan, satisfying the constraints, stability of the controller. Even if some of the little models that are being used in order to build the controller or do the estimator are learned, they're usually learned with a lot less data than end-to-end systems. They're more data efficient. But because you're doing optimization inside the loop here, they're usually less computationally efficient, and you need big computers, or you have to shrink the size of the problem that you can address. The learn policies, on the other hand, tend to be a lot more flexible. You encounter a scenario that you hadn't foreseen before, you collect more data, you do some learning, and then you're off to the races again. Whereas these structured optimization models are often very hard to adapt to new scenarios. They're usually more computationally efficient. Doing optimization inside the loop. You don't have to write more code in order to handle new scenarios, but you do have to collect more data, and these are usually very, very data intensive. A lot of attention has been paid to these end-to-end learn policies for a lot of these advantages, especially in terms of flexibility and efficiency. And people are talking about using vision language models to actually make planning decisions. And there's a lot of papers that are emerging around the idea that you can train an LLM to actually not just execute simple motor actions, but do complicated plans. Actually drive in sort of realistic city environments. But it's worth pointing out that whether or not, no matter what architecture you have, something always does seem to go wrong in the relationship between like the learn controller or the structured optimization and the higher level mission specification. A lot of the time, what happens is that we forget some kind of symbol, some important constraint, or we forget a state. Or we end up, for a learner, being outside the support of the training set, or something really unexpected happens. And so this video here shows an example of my students working with a Spot robot. And the Spot is a remarkably capable robot. This is arguably one of the best robots, or the best robot I've ever worked with. It's able to abstract away an enormous amount of the underlying environments. Like the robot does not need to know about the bags in the world in order to like pick its way across them. And yet, at the same time, something goes wrong when the unexpected happens. The robot stepped on a bag, and its interaction with the environment wasn't what it expected. It paused. The student in this case took the bag out of the way, but the robot knew it needed to get its foot out of something that was there. And then, unfortunately, the robot took a big step forward. It didn't understand its own model, and that giant step that it tried to take ended up knocking the bungee cord that was holding the battery in place off its position. The bungee cord came unhooked, the battery fell off, and the robot lost power. So this is an extreme example of the kind of thing that can happen when you don't get these abstractions correct or don't get the interaction between these different levels of abstraction correct. We know we need these abstractions in order to do efficient planning, in order to do efficient reasoning about the world, in order to do efficient learning. But at the same time, we have to think carefully about what these abstractions are doing for us and what the loss of information might be between these different abstractions. So that's really what I'm going to talk about for the rest of my talk today. I'm going to talk about how we actually address the loss of robustness that might come from these abstractions that give us computational efficiency and how we get that robustness back. I'm also going to talk about how these abstractions give us computational efficiency explicitly for the purposes of solving more complicated plans. And then if I have time, we're going to talk a little bit about learning efficiency and how we actually can use these abstractions even to learn more efficiently and drive down the data complexity of learned models. So let's dig in. The first thing I'm going to say is that these abstractions often give us uncertainty. That uncertainty can come in different flavors. You may have heard of out-of-distribution detection, where we have learned models that are trained on a set of training data, but then they are faced with a particular image that contains properties that weren't present in the training data. So I might train a semantic segmentation engine in order to extract the notions of the path and the grass and the trees and the sky. And those notions of semantic segments being on the path are really useful for the purposes of planning. I don't necessarily want to have to reason about like the entirety of the environment. Maybe I can like prune away the sections of the grass that I know I can't necessarily drive through and just plan local motions that know how to follow the gravel path through this environment. But I didn't train the semantic segmentation algorithm from the model on this puddle here. So it actually doesn't know about this puddle. And so that's the kind of abstraction that could possibly break in that my semantic segmentation algorithm might end up having to guess about what that segment of the image might be. But the problem here in this case is a little more complicated than that. There's actually there's a couple of different kinds of uncertainty, and the machine learning community right now is identified at least these two kinds of uncertainty. One is aleatoric uncertainty. So this is a statement about like the ambiguity of the actual target concept that I'm trying to get out of my query instance here. And so aleatoric uncertainty is really a statement that like the world is ambiguous and often stochastic, and I can't necessarily know exactly what everything is, even with all the perfect sensor data in the world. So it might be the case that like, my labels are noisy. Sometimes instances are ambiguous and reasonable people might disagree. Or it might be the case that like I actually can't tell exactly what the edge of this gravel path is. And so you get aleatoric uncertainty about like the ambiguity of exactly where the path ends and the trees or the grass begin. And so this is a thing that we need to deal with. There's also the case that we have epistemic uncertainty. This is where we're presented with something in our query data at test time that is actually not represented well in our training data. And so when we talk about uncertainty, we actually should be careful to distinguish between these two kinds of uncertainty, especially when we are abstracting away our raw sensor data into something that those more symbolic, higher level processes are going to reason about. So let's take each of these in turn. Let's imagine that we want to deal with aleatoric uncertainty, the fundamental ambiguity of the world. And here's another example of how aleatoric uncertainty, ambiguity can show up. Here's an example of a simulated drone navigating an environment, and it's picking up obstacles in its sensor feed down here. And it's detecting these obstacles, it's able to recognize the cars and the objects, etc. And it can even use its own motion to do structure for motion in order to localize these objects and even get a notion of its extent by basically, using sophisticated forms of triangulation around the bounding boxes of these cars, etc. And if you look carefully, I'm not sure how easy it is for everybody to see this image, but if you look very carefully, you can see the bounding boxes, the bounding cuboids, excuse me, do mostly line up with the detected objects, but they don't line up perfectly. And in some cases, the vehicle has actually flown relatively close, dangerously close, you might say, to the actual true extent of the object because the estimate was not very good. And what causes the estimate to not be very good is that we are ranging to these objects in the direction of motion. And so there's a real loss of observability as we move towards these objects as to exactly where they are and how big they are. Once we get some kind of lateral motion and we get a diversity of viewpoints, then we can get a much better picture. And so really what this is a statement is that sometimes we can see some of the properties of these objects and infer them, but sometimes we can only get a subset of them. So I can get great detections and I can get great bounding boxes without worrying about the ambiguity of where the object is. But until I actually have a diversity of viewpoints and I can actually get that lateral motion that allows me to localize the object and get a good sense of the bounding cuboid, maybe I shouldn't be actually trying to estimate the bounding cuboid. And we can imagine a hierarchy of abstractions. I initially get like just bounding boxes, and then I get a couple of measurements, and I can get maybe not bounding cuboids, but I can get bounding spheres that tell me that there's an object here somewhere, and it's at least as big as, or it's not bigger than some bounding sphere. But I know I need to stay a reasonable distance away from that object until I actually know exactly where it is and how big it is. And we can organize these models at decreasing levels of abstraction as I get more and more information. And we can actually we can solve the inference problem over the spheres and the bounding cuboids and whatever else you might want as a least squares problem, where the condition number of the linear system is either well-conditioned or ill-conditioned for the number of degrees of freedom that I'm actually performing inference over. And as I get more and more sensor data, I can basically move them up and down the hierarchy. And we can see this in effect here. On the left is the same video I showed you a couple of slides ago. And on the right is our technique for actually reasoning about what is the right level of abstraction for representing these objects as a function of the aleatoric uncertainty, as a function of the loss of observability that comes with basically ranging along the optical axis that's aligned with the direction of motion. And you can see in some cases that we actually wait a long time before we can actually get a confident estimate of where the object is and how big it is. But if you compare the ground truth objects in the dark gray cuboids on the right versus the left, you see you get much better alignment with the estimate in the colored cuboid and the ground truth in the dark gray. But even better is that the trajectory of the robot is much more conservative when it doesn't know where the object is. And so the abstraction basically says what assumptions we can make or what statements we can make about good and bad plans as we move through the environment. So this is work that my students Kyle Hawk and Catherine Liu published a couple of years ago. So that's how we can reason about abstraction and how much we know about the environment as we make as we perceive the environment and we infer these models. But what about epistemic uncertainty? Those bounding cuboids and those bounding boxes out of the images were, of course, large models. And I gave you the example earlier of the puddle that wasn't present in the training set for our semantic segmentation. How do we deal with epistemic uncertainty? Let's imagine that we have our semantic segmentation network that's doing, say, pixel-wise semantic segmentation, distinguishing between gravel and trees and the sky, et cetera, and it's presented with this patch of the image. Well, it's relatively straightforward to make our most learned models output some kind of distribution over the classification set of labels. And you can imagine that this distribution is a distribution over possible errors, maybe. The unfortunate reality is that deep networks in particular really build their entire representation in order to capture the entirety of the training data. And so a lot of the time, there's no actual expressive power left at the very early features to represent the kind of data that is out of distribution. That this is really a statement that given that this is in distribution, this is the possible error, but it doesn't have any expressive power or any statement about the likelihood that this is actually far from the training set. So what might we do about this? Well, there's been a lot of attention paid to flow models and diffusion models, especially in the last few years in machine learning. And there's this notion of actually representing the density of data using flow models. So normalizing flows in particular give us a way to estimate the likelihood of our latent features under the training distribution. And this is well understood technology. Normalizing flows allow us to assume a base distribution, say a unit variance single mode Gaussian, and we can actually learn a model that transforms or transports that base distribution using one of these flow techniques to actually be a distribution over the feature representations. Now, it's not reasonable to expect that the features of all the images that we would see in our latent space would in fact be univariate Gaussian. But what the normalizing flow does is basically transforms that Gaussian so that it more accurately represents the input distribution on our features. And then we can combine the likelihood of this, say, query image under the normalizing flow to give us an estimate of this basically gives us a density estimate over the latent space. And we can compute the likelihood of a query under that training distribution. And we can combine that likelihood of the query, how likely this query image was given the training data, with the likelihood of the output of the semantic classifier. And this gives us a likelihood of the actual label, weighted by the likelihood that we actually recognize this image. Unfortunately, there's a couple of problems here. First of all, yes, I said that it's unlikely that the distribution of images on this latent space is a univariate Gaussian, and we've fixed that with the normalizing flow. But in reality, most images on latent spaces are distributed not according to even unimodal Gaussians. We actually need to do something about the fact that this is probably a multimodal distribution on the latent space. And the second thing that we need to deal with is the fact that this feature, we're representing the likelihood of our query images on this feature representation. But I already said we trained our feature representation in order to basically maximally express the training distribution. And so we might have no expressive power left on our features for images that are very far from the training set. This is essentially a form of perceptual aliasing. And so we need to make sure that our underlying features aren't going to be subject to perceptual aliasing, where we can't tell at the feature level between an image that is in the training set, and an image that is outside the query set. So what do we do about this? So the first thing that we can do is that we can actually just say, you know what, actually maybe our base distribution isn't a single univariate Gaussian, but it's a Gaussian mixture model. And we can try and express our training distribution using a small number of Gaussian mixture models. I'm not going to say much more about this. This is relatively easy to do. But the other thing that we need to do is that we need to modify our latent features to make sure that we're not going to be vulnerable to perceptual aliasing. And the way that we do this is that we're going to add an extra loss to our training set so that when we train our latent features, we're also going to make sure that they're good at reconstruction. And we're going to add a reconstruction loss. And what this does in practice is to basically make sure that we have latent features that are good at the main task of semantic classification given the training data, but they're also good at reconstructing all the images that they've seen. And so if we train add a patch reconstruction loss, then we're going to get a set of features that are very good at representing a wide diversity of images. And we're also, if we have a Gaussian mixture model, it's going to be empirically pretty well aligned with capturing how images are distributed. And so we trained a normalizing flow model to give us with a multimodal base distribution and with the additional loss function. And then we look at these images, and what we see is that in this environment, we're actually getting a very strong essentially what we're doing is we're lighting up the pixels that correspond to being out of distribution. And we've never seen a building. This semantic segmentation was trained entirely on these forest patches. It didn't know about puddles and is lighting up in exactly the places that we would like. What's going on here is we're getting a log that's actually distributed not as the trees, which are normally vertically oriented. We're lighting up on the cars, the buildings, and the trees that have fallen over that weren't in our training set. And we can do the same thing in urban driving as well. We get the patches that light up for the kinds of things that we haven't seen before. So how do we use these uncertainties? So I've made the point that we would like to have some notion of when our abstraction in terms of semantic segments is useful, or maybe when it's uncertain because it's maybe not present because it's ambiguous according to our aleatoric uncertainty model, or because it's uncertain because of epistemic uncertainty. We're presented with part of the world that we don't have a good model of. How do we incorporate these uncertainties? So one thing that you could do is you could simply say, I'm not going to trust parts of the environment that are highly uncertain, that they're a long way from my training set. And so that's fine. But as we explore the world, we might end up encountering the scenarios a lot of the time where we don't really know what to do. And that's really going to limit how much we can operate. The second thing is that a lot of the time we might have some idea from another model. So is there a way that we could actually combine a learned model that says, okay, I'm looking at a part of the environment I really know well, I know exactly what to do, with some kind of more conservative but physics-based prior that says, okay, the learned model doesn't know what to do, but I'm going to back off to a more conservative model that still says what to do. I'm going to, actually, I'm going to be more conservative in my motion, but I'm going to actually use some knowledge of how the world works in order to make progress here. So this video here shows an example of a robot encountering a patch in the environment that it's not seen before. It's never seen that. It only knows about flat floors. And so if I play that video again, it said, I don't know what this ramp is, and I don't know what this uneven terrain is. And so I'm just going to pick a trajectory that's off to the right here. And, and it does an okay thing, but it does go a long way out of the way. On the other hand, might be very conservative. If we had terrain that's unseen during training, but we have a physics prior that says, well, actually, this looks flat. And so even though it's sloped, and so my learner doesn't know what this is, my physics prior actually knows what it is. And so what we get is that the physics prior is able to actually back off to at least the part of the environment that it says, I actually know how this part works according to physics, and I'm able to do it reasonably well. And so what I'm advocating for here is that if we actually have a model of different kinds of abstraction, whether it's a learned abstraction or a physics-based abstraction, if we actually have rich models of uncertainty and how much we can trust the different representations, then we may get better performance overall. Um, Now, the pixel wise segmentation worked very well in a lot of scenarios, but it might be the case that there's actually parts of the environment where we actually need to segment out parts of the environment for the purposes of learning. So I said I wouldn't talk that much about more efficient learning, but this is one of the places where we actually do want to actually identify parts of the environment, parts of the world where we know there's something unfamiliar. Can we extract that for the purposes of going to like a Oracle or a human partner or something and saying, help me label this? And so this is a little bit of a different result than what I was just talking about. I still think it's interesting. I just wanted to share this with you, is that could we actually take our pixel-wise representation of uncertainty and extract the distinct entity that is uncertain for the purposes of like improving our learning? And without going too much into the details of this, the postdoc that I was working with at the time, Sid Ancha, who's now a research scientist at Berkeley, he had this idea that we could actually use diffusion models to actually resynthesize the scene, and then actually compare the resynthesized model to the original input image, and use that as a way to extract distinct entities in the environment that might be unfamiliar. And so imagine that I take that same forest scene that I was showing you earlier, and I might have a very distinct part of the object. In this case, this is like a wheeled vehicle that it's never seen before. And if we've trained this diffusion model, we can actually reconstruct the entire image and say, you know what, this patch of the image is uncertain. And then if I do a comparison, I can say, there's something here that I don't know about, and maybe I need to learn this. And there's a number of steps that we had to go through in order to get this to work. But we trained a diffusion model. And what we were able to do, this is exactly what's happening here, is that the diffusion model, conditioned on the input image, reconstructed this forest scene here. And then we wanted to say, well, what exactly changed? Pixel-wise differencing didn't actually work very well. But if we fed the two images through clip, and then we actually re-upsampled those clip features, we got images that look like this. And then if we ran SAM on top of those clip images, then we actually get the segmentation on the images that look like this. And all of a sudden, the SAM post-processing highlights this distinct image, this distinct object right here, very, very nicely. And what's really interesting is that we get surprisingly good performance out of the diffusion model. The clip features are at the diffusion plus clip plus the feature reproduction of the original image, and then running SAM on top of it gets beautiful extraction of these objects. The diffusion model is very slow, so I don't want to pretend this is real time, unlike the pixel-wise segmentation that I was showing you earlier that was real time. But we're essentially predicting anomalies using synthesis by analysis. And so we're discovering abstractions in our sensor data that are really anomalous that we can then pick out and do something with. As the video continues, you can see we also got good performance in very different kinds of environments. This is underwater data. This is courtesy of Travis Manderson and Greg Dudek and McGill. Travis was working with SID and had this data set and showed that we could pick up anomalies in the underwater data as well. So very hard to incorporate this in a planning model in the way that I did with the pixel-wise detection. But you could again imagine highlighting this for a scientist underwater, or highlighting this for a human partner, saying, "Here's an anomaly. My abstraction is broken. I need to know what to do about this. Help me learn something about this." So fundamentally, abstraction with appropriate models of uncertainty let us reason efficiently about what we do and do not know. And so this is one of the advantages, or one of the things that we need to pay attention to in addressing these shortcomings that come from when the upper level models don't have are operating on abstractions of what's really going on at the lowest level representation, closest to the robot physics and the world geometry. Okay, so how do we use these abstractions for the purposes of computational efficiency? So I've made the point that part of the reason why we have these abstractions is so that we can get more efficient planning and can carry out more complicated missions. And really, the question that I want to ask is, like, if we have a robot that's planning in an environment, so imagine we have our spot again, it's equipped with an arm, and we give it tasks, like it's got to move through the environment and it encounters a blockage in the environment. How could this robot reason about discovering the object in the environment, and then it can pick it up and move it out of the way in order to continue moving through this environment? The first thing that we need is a representation that corresponds to this kind of symbolic representation. We need to know again about objects in the environment, and we need to know about perhaps places in the environment and what it means to pick an object up and move it out of the way. How are we going to get a kind of representation of the environment that allows us to do this? We've been working, I and my students, we've been working closely with Luca Carloni, who's very conveniently down the hall at MIT, and his students. And Luca's been working for the last few years on this structure known as a scene graph. So those of you who know Luca know that he's very well known for tremendously great work in mapping and SLAM. And one of the things that Luca had noticed is mapping and SLAM itself is very computationally intense as we increase the length scale and the space of operations of our robots. And so really some form of abstraction is required in order to break the world up into places and rooms and buildings and regions of the world, primarily for the purposes of efficient inference. And in collaborating with Luca, we've recognized that hierarchical structure is also super useful for efficient planning as well. And so Luca has developed this rich technology that breaks the world up and builds the low-level geometry of the environment, but it can also detect objects and build object meshes, and then break the world up into places and rooms, etc. For the purposes of planning, we can convert those objects and places, etc., exactly into predicates of objects, where they might be in the world. So we can the relations between the objects and the places they might be, predicates that describe how the world is connected. And if you're familiar with task and motion planning, then this kind of logical representation is often how we express high-level task plans that then get converted into motion plans. How do we do the conversion into motion plans? Well, by virtue of having the scene graph, we have the low-level geometry, and all of a sudden we can run motion planning algorithms to get us from place to place in the environment. And this is very reminiscent of some work that we did a few years ago with Hadas Kreskazit and her students. And so Hadas is, one of the people that we really look to for a lot of the work or a lot of the key ideas in how to plan in these kinds of logical representations. One of the challenges that we encountered in actually starting to bring in Luca's work in scene graphs into our task and motion planning algorithms is the fact that the scene graphs are great. They're highly accurate, dense geometric representations that have this nice abstract representation layered on top. But just as I argued that the kitty representation of the environment was simultaneously both too simultaneously contain too much information and not enough information, the scene graphs also tend to be very, very rich representations, overly rich for the purposes of planning. The number of high-level task skeletons, before we even convert them into motion plans, tends to explode, even for simple representations like this, which is the sixth floor building 45, where Luca and I have our offices and our labs and our students sit. This is, if I take away the low level sort of appearance information and dense geometry, we're left with an abstract representation in terms of places layer and where objects might be. But this representation still tends to really stress the planner. A relatively efficient planner still tends to take an undue amount of time in getting to efficient plans. And so two ideas that we pursued here are, how do we get a sparse abstraction from, so we have a great abstraction coming to us from the scene graph that abstracts away the dense geometry, but we need a sparse abstraction that's aligned with the needs of the planner. There's going to be objects in here that are irrelevant to a particular task that needs to be completed. And there's also going to be places in the environment that are relevant to the task. So how do we actually derive that sparse abstraction? So two ideas here. One is that we can identify redundant symbols. So it might be the case, for instance, for most missions that we need to complete. A lot of these places here that are important for preserving the correct geometric and metric properties of the environment, they're kind of redundant for the purposes of planning. And so we might be able to merge these. So that's one idea, is that we have some formal algorithms that can identify redundant symbols and ensure that we preserve planning guarantees. And the second thing is that we have algorithms for identifying missing symbols that are heuristic, but very efficient. And then when we fail to find a plan, we have techniques that allow us to basically re-add those missing symbols into the representation and replan. This may very well be one of the next most important problems in actually getting complex mission execution out of real robots derived from perception, is that this notion of like building a representation of the world that's aligned with the needs of the planning system is really hard. And other people are starting to look at this problem too. So folks like Tom Silver at Princeton and Alberto Nad and I think University of Toronto and colleagues have been looking at exactly how do we actually build partial representations from a fully grounded symbolic representation. And so this is an example of us using exactly this task and motion planning on top of a scene graph, where we took that building 45, sixth floor representation, and we gave the robot the goal of like being able to visit an object to a particular place while making sure that it's safe. We identified that certain kinds of objects were safe or unsafe. The robot's able to recognize this object who's in its way, and it's able to move it out of the way in order to free up that passage through the environment. And this, we're continuing to build. This is one of the first results we had at the end of 2024. or 2023, excuse me. And we're very happy that we're able to get these kind of complicated plans out of this environment. And we're starting to increase the size of the environment that we're dealing with. We did some experiments at University of Pennsylvania a couple of weeks ago. We are building like rich scene graphs over like, hundreds of meters in and around buildings. And we're able to execute these kinds of plans relatively efficiently. And we see the impact of the sparsity of the representation on the planning time. So if we have, these are three different kinds of planning environments, a very simple alleyway, a 10 by 10 grid, and then an indoor scene graph. And you can see that for the different kinds of problems, the alley, as we give it different kinds of planning problems, there isn't a lot of gain to be had in terms of planning time between a sparse formulation and dense formulation because the problem is already pretty sparse. If we sparsify it, then we see that we get if we get from 10 to the -1 to 10 to the 0, we get an order of magnitude speed up for different kinds of problems. And then the indoor scene graph, we see that we go from 10 to the -1 to 10 to the 2, we get 3 orders of magnitude for certain kinds of problems in this indoor scene graph by explicitly sparsifying the graph before planning. So that's great. This sparsification is super, super important for actually getting good behavior. Of course, as what we see is like as the problems get more complicated, the value of sparsification does tend to go down. As you need to interact with more and more objects in the environment, then you spend as much time thinking about sparsification as you do actually planning. So it's not a silver bullet. If you have a genuinely dense planning problem, then you need a genuinely dense solution technique. A question, of course, you might ask is that, given those logical representations and the scene graph has this notion of places and regions, and Luca and his students give us this rich ability to actually reason about places and regions, where does the notion of region come from in the first place? How do you know you even actually have the right symbols in the first place? And this, I think, is a really, really interesting question. It's like, can you actually automatically derive a symbolic representation from the lowest level sensor data? And so we have some very preliminary results in this area. But imagine that you're a robot just navigating in this like really, really, really trivial representation. But you're just watching the robot, take forward actions and stop, and before it gets into collision and turns, etc. You can actually examine the velocity traces of the robot as it moves around in this environment. And you notice the velocity traces kind of segment into places where, we accelerate quickly and then we slowly decelerate, accelerate quickly, slowly decelerate, and then we turn, etc. And if you apply appropriate clustering algorithms and designed to force those clusters apart, then you can actually get a recognition of when the robot's moving, when it's not, when it's turning in different directions, which is super interesting. And so we can actually build a clustering on the velocity signal. And then you give those clusters to an LLM and you ask the LLM, what do these different velocity clusters mean? And we actually have to do a little bit more clustering on the LLM output as well in order to find good linguistic descriptors of the clusters. But we actually end up through this process of looking at velocity traces, getting at exactly the kinds of thing you'd think, which is we get clusters that correspond to moving forward, turning clockwise, turning counterclockwise, and standing still. And then you can actually give a natural language prompt to the robot to actually take that kind of abstraction and use it to plan. Really, really trivial problems that we're dealing with right now. But we can actually say, okay, I'm in this maze world, and I've got these symbols that represent my motion. Can I actually generate a plan that stays only on the white squares? And then can I take that same representation and give me the same representation, but only stay on the black squares? And we can go from watching the lowest level representation of the velocities to clustering those to actual symbols that represent motion to different kinds of planning problems. You contrast this with a pure end-to-end learning approach, and you can see that the learner can actually learn to control the robot in order to stay on the white squares. But then we flip the meaning of the problem and say, please stay only on the black squares. The learner basically takes a giant hit in performance and then it has to relearn a whole lot of the world before it can actually get back to the same level of performance with inverted colors. Whereas we can basically do it in one shot. We can basically tell the robot, this is what the symbols mean now, this is your goal state, and it's able to plan immediately. So I suppose when I talk about this particular architecture here, I guess I am, or I describe that trade-off between the two different architectures. You have end-to-end learning on one side, and you have the structured optimization on the left. Um, this figure here kind of reveals my own bias, which is that I think that there's some value into having some structured optimization and some kind of high abstract representation that allows you to actually add domain knowledge that describes how the world works and how the world might change, and very efficiently replan in that new representation of the world. And then very quickly react to that, as opposed to in the end-to-end world where you would have to like automatically detect the world had changed, and then you would have to allow your learner to adapt. And that could be very powerful if you don't actually know how the world changes. But if you knew how the world changed, you might actually like to be able to just use structured optimization to adapt very, very quickly. But you better recognize all of the challenges that come with the fact that you have abstractions at work here that can induce uncertainty and that can induce computational cost if you're not careful about not careful about representing that uncertainty and not careful about aligning the abstract representation with the needs of the planner. Um, how am I doing on time here? I suspect that I'm pretty close to needing to be done for Q&A. Is that right?
Yeah, but you could still take like a couple of minutes. Just make sure it's a fine to finish it because it's
Okay.
cheap. So
All right. Well, I'll just, I have the last thing that I want to talk about is learning efficiency here is that, and I'm going to go through, I'm going to skip over a lot of the technical details here, but just say that like, uh, a lot of these models are built on top of learned data. So when we talk about state estimation and we talk about controllers, a lot of the time we're doing things like system identification in order to learn those underlying models. I talked about semantic segmentation. That is certainly built on top of learned models. And one super interesting thing for me and my students has been to recognize that like the abstraction that allows us to connect the lowest level sensor data to high level symbols can also provide some notion of learning efficiency, which is kind of surprising that abstraction would actually let you be more efficient about how you learn. So let me give a very simple example. Imagine that you're a robot that's going to manipulate blocks. And so you can imagine training a robot in order to learn how to pick up these different blocks that have different dimensions. Some of them are like just strict cubes, and some of them are, more oblong in shape. And you might actually learn a policy that says how to pick these objects up and how to stack them, etc. But let's imagine that I actually messed with the blocks in some way. And I actually gave the blocks very weird centers of mass. I might internally move put a mass inside that like makes the object very stable, even though it's got some long overhang, or makes the object very unstable, even though I think it's mostly balanced over top. And so what's happening here is that like I might learn that I can put objects one on top of the other so long as I have like, the sort of the center of the body over top of the support area. But if I have a weird center of mass, then my abstraction is going to break because this might actually be stable, but it might actually be very hard to construct. And so how do I actually allow my abstraction to understand that there's more going on at the very lowest level here? Well, one thing that we did was we actually like gave the robot a bunch of these objects and said like learn about these objects and learn how the centers of mass actually vary across these different objects, and then learn how you might actually stack these different objects. And we let the robot, this is essentially like an arm farm type idea. And it had all these objects had April tags on the side that allowed the robot to uniquely identify each object. And it was able to learn like how the center of mass actually varied with each object, and it could learn how to do different kinds of stacking and tasks, etc. Over 55 hours, relatively slow process, but it worked relatively well, and we were able to like get some measure of efficiency of how to learn to do these things well. But what if we don't know the dynamic model parameters? What if we can't observe the center of mass from passive imaging? Do we really actually have to learn how to grasp every new configuration, each new object from scratch? And the answer is no. Because if we actually learn how centers of mass might actually vary, then maybe we can actually factor the problem, factor abstraction of grasping into the basics of just like mechanical grasping and learning how to actually adapt to the center of mass. So I don't have to learn how to grasp every new object from scratch. What I need to do is I need to learn how to grasp, and I need to learn what centers of mass mean for the purposes of grasping. And so by factoring the representation into grasping and adapting to different objects, I can adapt very, very efficiently. And humans do this very naturally. So this image here isn't of blocks. This image is of different hammers. And most of us are familiar with the idea of like picking up a hammer and kind of hefting it a little bit to figure out how heavy it is and what it's going to mean in order to swing. And you don't swing a very light hammer that's maybe for finishing nails the same way you swing a very heavy hammer like a sledgehammer. But the basic swinging and hammering action is basically the same. You'll learn how to do that. You'll learn that as a kid when your parent gives you a tool to play with. But then as you get older, you sort of learn how like these different hammers behave and like what it means to interact with them. And we've been able to get that same kind of behavior out of our robots. So this is a robot that is learning what it means in order to actually like grasp these different objects. And in this case, it's actually adapting. And it's able to adapt very, very efficiently. One of the things that we did was we showed we could use learned models to actually drive that adaptation much more fast, much more quickly than if you were just doing straight out of the box inference on some kind of like latent manifold. And so it interacts with these objects over a while, and then it's able to actually build get an understanding of the object, and then it's able to build different structures of the kind that we give it. And I'm going to skip over how we actually do this inference relatively quickly, but we're able to very quickly learn how to grasp these objects stably. And the abstraction lets us reuse the parts of the model and learn just the new parameters as needed. And then we're actually able to do relatively sophisticated assembly. What's cool about this particular video here is that we actually showed that we could put together a lot of the different things that we've been building in my group, which is the high level symbolic task planning coupled with the low level models of skill acquisition in order to build a relatively complicated planetary gear mechanism here. And what's also super interesting about this is that we were actually able to learn the appropriate abstractions in simulation. And then we were able to show how we could transition that simulation, that learned simulation, to an actual real robot, even when the learned simulation wasn't necessarily physically realistic, by actually capturing how the simulation was going to differ. The simulation, which is in itself a form of abstraction, is going to differ from the real world. We can actually learn policies that are robust to those differences and execute them on this relatively complicated mechanism where we're dealing with like threading nuts, and we're aware of the problems of cross-threading, and we're aware of the challenges of getting these gears to mesh, and we're able to build this mechanism in a way that's really, really nice. So just to wrap up here, hopefully I've convinced you that most, if not all, real robot systems, in order to carry out complicated missions, are relying on abstractions that allow the robot to reason at different representations of the environment. But those abstractions are necessarily imperfect. And so there's losses of performance that can come if you're not careful about what you represent at the boundary between these different representations. And so things that we need are being able to actually model the uncertainty that can come from these abstractions. We need to actually reason about what is the right information to extract from the lowest level representation to allow planning efficiency, and how do we actually factor these models in order to actually get computational, not just computational efficiency, but learning efficiency. And we know we need these abstractions. We know we're getting at good ways of getting these abstractions. And hopefully these three principles of learning efficiency, robustness, and computational efficiency can give us new ways to actually make more robust and efficient robots. This work is, of course, the result of many students and postdocs that I just want to acknowledge here, and also acknowledge I had great support from a number of sponsors, for which we're very grateful. Really appreciate the opportunity to come and talk to you about the work that I and my students and postdocs have been doing over the last few years, and I'm happy to take any questions you might have. Thanks very much.
Thank you so much, Dr. Right. It's a pleasure having you give a talk here. And excuse me. There are a couple of questions. Like the first question is, could you please elaborate a bit more how to learn physical model, the prior for the physical model?
Oh, great question. So I assume that you're describing this work here, where we are using the prior physical model combined with it. So the prior physical model is not learned. So the entire point of this is that we describe a physical model of like how to work, how to walk on flat surfaces, or maybe how to walk on inclined surfaces. Very, very simple. Would not be sufficient for walking across this very uneven terrain. So what we're doing is yeah, in this case, it's like a relatively simple flat plane model with some ground reaction forces. And then there's the learned model for walking across this uneven terrain here. So the point is not like how we learn the physical model, although I suppose you could, but we didn't in this case. We encoded by hand what we knew to be a good model for working on certain kinds of like terrain derived from physics. And then we had a learned model for walking across more complicated terrain.
Thank you. The next question is, how does the system make sure the meanings from its clustered actions stay consistent when the robot learns new actions later?
Ah, that is a good question. I don't have a good answer to that. Um, you know, so there's two possible concerns that you might be pointing at. One is how do we actually make sure that like as a robot acquires a new skill or learns a new concept, it's actually interpretable to an outside human? I don't have a good answer to that. And one of the things that I like to do is to collaborate with human factors people like Andrea Bobu and Julie Shaw and others, and that's a huge open question. The other question you might ask is like, if you're acquiring new concepts, how do you make sure that they're well aligned with the existing concepts? So, so long as you're always adding new concepts, then I don't think that you need to worry so much about concept drift and like inconsistency with existing concepts. What you might need to do though is in the space of finite resources, making sure you have a model of a finite size. Like, how do you associate a new concept with a previously learned concept? That's a good question. I don't have an answer to that either. So great. More work to be done.
Thank you. The next question is, I'm wondering whether this hybrid representation framework could be extended to multitask decision-making settings, or if there is already any connection between this and multitask learning.
So I'm pretty sure there is a connection to multitask learning, but I'll admit that I don't know what it is. So some of this work is in conjunction with Leslie Kelbling and Tomas Lozano Perez and their students, and they've done a fair amount of work on multitask learning too. I think there's an important question to be answered, which is for some tasks, how do you decide when, a bunch of different tasks are all related and you should just use multitask learning to generalize across those? And when do you actually need a fundamentally different model and you need to switch to that model? There are people who have looked at like mixtures of experts that I think like try and get at that, but I don't know the answer. And I think that Leslie and Tomas are people who and their students are looking at that. And I don't have a better answer than to say that like we should probably go and look at some of the work that they are doing in multitask learning.
Thank you. And just more of a personal question, like, so when you sort of combine the learn model with the physics informed model, like, so I'm curious whether like uh, multiple agents, like what if like one agent is at a different orientation, maybe that agent is able to see the same thing in a different perspective, and
Yep.
like could like multiple agents sort of collaborate in some sense because they have different models. Just curious about that.
No, it's absolutely a great question. And to a large extent, that's what these experiments have been designed to elicit is that when we do these experiments at West Point, we are doing them with multiple robots, and we are explicitly trying to reason about these are not the same robot. The one on the left is a legged robot with an arm, the one on the right is a wheeled robot without an arm. The wheeled robot on the right is capable of more payload, so it can carry more compute. So we are trying to explicitly reason about like the different capabilities of the robot and who can do what. We are also definitely sharing information and trying to get at the question of how do you fuse these representations. You asked a question about like different viewpoints. We have that is absolutely a problem that we're aware of. And we are trying to develop algorithms to solve that. I don't have much to say right now, but it is a real need. And anybody who has thoughts about how to solve that planning problem better in terms of like, how do you aim the sensor viewing frustum from these different robots in order to get the best joint situational awareness? That's a great question. One we're very, very interested in trying to tackle right now.
Thank you so much, Dr. Rai. I think that's all the questions we have for you today.
Very good. My pleasure.
Uh, it, it
Thank
was
you.
a pleasure having
All right. Thank you so much. Bye-bye.
you.